for joining us today. This webinar is being recorded and the recording has started. We are pleased to be presenting this webinar at the culmination of one of our Habitat Strategic Initiative grants, completing High Resolution Change Detection, HRCD 2015, and extending through the 2017 National Agricultural Imagery Program flight. My name is Jennifer Griffiths, and I co-lead the Habitat Strategic Initiative. Washington Department of Fish and Wildlife and Washington Department of Natural Resources are currently serving as the Habitat Strategic Initiative lead through a cooperative agreement with EPA. We award grants through the U.S. EPA National Estuary Program, Puget Sound Geographic Funds, commonly known around the Puget Sound as NEP funds. Our grants are to near-term actions, NTAs, in the Puget Sound Action Agenda around estuaries, floodplains, land development and cover, and shoreline armoring vital signs. NEP funds are a unique funding source that have a special niche contributing to Puget Sound recovery. This NTA was selected for funding by the Habitat Strategic Initiative Advisory Team because it is directly advancing and implementing the Land Development and Cover Implementation Strategy. The Land Development and Cover Implementation Strategy is a roadmap for achieving some of the vital sign indicator targets. The work under this NTA tracks changes in land cover over time with accurate, high-resolution spatial information to be used by local jurisdictions, state agencies, tribes, and other organizations throughout Puget Sound. These datasets form the basis for tracking several new Puget Sound vital sign indicators adopted by the Leadership Council in 2020 and has applications for all the habitat vital signs. The Habitat Strategic Initiative is committed to sharing the work of our grant program to advance Puget Sound recovery. We are really pleased to have Ken Pierce from his home office with us. Ken is with WDFW's Habitat Program Science Division and leads the Landscape Spatial Analytics section. He has a PhD in landscape ecology from Duke University and held a postdoctoral research position with the U.S. Forest Service before joining WDFW in 2007. Ken has worked to make vast improvements to the information available at scales relevant to local jurisdictions as well as to the region. He will share an overview of the data, analysis to date, and as well as opportunities for different ways this information can be used for a variety of land cover change questions. With that, I'll turn it over to Ken. Thank you for joining us.
All right, am I on now? Yeah, thank you, Jennifer. I was muted. All right. So thank you for having me this morning. This represents the work of myself and my team, and we're just going to jump right into it. So the change detection program really started in 2009 when the USDA presented Washington with their second year of high resolution imagery. And in response to that, the Salmon Recovery Funding Board awarded DFW a grant to try to figure out what we could do with that imagery to be useful for habitat monitoring. And what we came up with pretty much was that change was the primary thing that we could do repeatedly and accurately over time. Since that time, the EPA, through the National Estuary Program, has continued to fund our project. And as we've gotten new NAEP data for 2011, 13, 15, and 17, we've continued to provide this service. Okay, the thing that really sort of sparked the idea here was the difference in resolution. That most land cover monitoring at regional scales is done with 30-meter data. And it's done as both change and land cover modeling. And that's good for broad regional areas, things like forestry or large land management, but it doesn't work as well for urbanizing systems. As you can see here, what we're trying to use is the 1-meter resolution data on the right. You can kind of see the specter of a road somewhere going through the 30-meter data. But it's kind of a mishmash. It's hard to see what's actually going on. So the HRCD is primarily been has 3 types of data as of today, but it's primarily been a change detection program. And we, over the 11 years of data, have produced, and by 11 years, I mean 2006 to 2017, about 250,000 verified change locations for the different time periods. And today I'm going to talk about that for a while, but then we also have 2 new data sources, and those are our 2017 canopy maps and the surface water maps, which we'll get to at the end there. If you look at the number of changes per time period, they are stunningly similar up until the last one, and frankly, I was really happy to see something that didn't that veered from the trajectory so far. Being off, the first two time periods being off by 13 was just weird. Okay, change polygons. I digress. The real thing when we look at change, we're looking at two things. We are looking at decreases in canopy cover and increases in impervious and semi-pervious surfaces. And change can be all sorts of different things, but when you really gets down to the application of what we're mapping, it's these two quantities. And how the process works, I'm not going to go through the statistical part, but a bunch of modeling goes along in order to get to the point where we have locations that we think are likely to be changes. And then once we have those locations, an analyst looks at every one and looks at the pre and post date of our time interval, and then selects attributes a variety of things. We have 4 primary quantities, which is the overall change percentage, the decrease in tree cover, increases in impervious surface, and increases in semi-pervious surface. Unique to those 4 things are unique to this product, but we also record an idea of what the change type was, or the change agent, to give an idea of why it occurred. And a repeatable starting land cover, and these things will all become a little more obvious as we go through the presentation. Also want to say at this point, there's a lot of nuance to doing analysis with this data. It was designed to be simple, but I've been told for the last 10 years it's not, and I suppose it isn't. And that is partly because we have a lot of attributes associated with the data, and you can do a lot of unique things with it. And we'll come back to the idea of nuance towards the end of the presentation. So this is what an analyst would do. They'd look at these 2 locations that would be denoted by a polygon that's drawn by the computer as to what it thinks is a homogeneous area. This particular example I've been told to stop using, and I will probably change it because it's actually a mixture of multiple changes that got aggregated together. But you might say the average change here, total change is about 50% of the area, and you may think it's 100% when you quickly look at it, but there's a lot of surface ground that really hasn't changed any. Tree decrease here is around 25%, and impervious increase also around 25%, notably not in the same locations, which is why you have the changed area that's wider than the individual percentages. Change type development, which we pretty much have anytime we have new impervious surfaces, about 4.5 acres, and the initial cover was mixed cover, non-built. Okay. Change agents. Change agents are unique to our product and allows you to look into different reasons for why things occur. We have the 4 biggies are development, forestry, tree removal, and stream natural. And the other 4 sort of come along. This particular graphic is from our cheat sheet, which you can download from our website, which I will allude to again a few times. So just as a sort of as an initial thing, why do we do this? Well, turns out over half of our change locations are tree removal, and a pretty large number of them are development. Forestry, which is, we'll see in a few minutes, is by footprint, by total area, is about 70% of all change, but is definitely not 70% of the locations. And this goes back to the reason for the resolution issue. Forestry winds up being an overwhelming, has a huge impact on change, and actually picking up all the things that are smaller is a lot tougher, which is why we use the data we use. We also have initial land cover, and so the initial land cover does not conform to any actual land cover types, but it's basically a way for us to have an idea of what was there before the change started. And so this is also on the same cheat sheet, which you can download, which says what our different covers are. But we can see, look at the bottom here, I have some statistics, and mixed, not built, which is basically a mixture of miscellaneous mixture of trees, grass, and shrubs and bare ground where none of them are more than 90% of the location is our most common pre-existing condition of 91,731 locations, and forest cover is the second. Now, forest cover in this case really just means that the polygon of interest has greater than 90% tree cover, and so if the polygon of interest is around 4 trees in somebody's front yard, that'll get called forest because in that small context, it's a forest. Okay, so some statistics. We measure these 4 different quantities: impervious, semi-pervious, canopy loss, and right here, I split out forestry, and so let me discuss that a little bit. This graph started off as just the first 3 quantities, impervious, semi-pervious, and canopy loss, because that's what we actually measure. But forestry as a change agent is almost entirely canopy loss and doesn't have that much new impervious or semi-pervious based on where it is. So I wanted to split that out specifically, and so forestry is pretty much also canopy loss. And here we can see again, and this I find surprising, specifically how much time and effort has been put into this, because it's done as for each time period, we do it as 19 different study locations, and so it's a huge amount of separate things, and the fact that it comes out to such consistent trends is stunning. So maybe sampling would work better at the maybe sampling works fine at the regional level, but the nuance of the individual locations are quite varied. If we look at counties, we could just look at total number of changes in different counties. And here I normally use RIAs because we have full RIAs. But one thing to remember is that not all of these counties are entirely in Puget Sound. So Lewis County, for instance, that is a tiny, tiny piece of Lewis County. There's a lot more going on in Lewis, but that's just the tiny Puget Sound portion. Let's see, Jefferson, Clallam, Mason, all are Whatcom, or all, no, Whatcom's all in Puget Sound. The rest of those are all only partially in Puget Sound, and so when we get down to Kitsap, Thurston, Whatcom, Skagit, Snohomish, Pearson, King, those are all entirely Puget Sound areas. Then we could look at actual change rates. So this is just the number of events measured. If we look at change rates, they're all over the place, but they tend to be pretty small. And so the annual change rate by area is almost always less than 1%. Jefferson, I think we'll see, has quite a lot of forestry in the area that is covered in the portion that is in Puget Sound, and we can kind of see that in another slide or two. So that makes it a little higher, but pretty steady rates. And these this is for the 2015 to 2017, but this is the order of magnitude for sure that continues from year to year. In the analysis area, I should note in this particular context is the extent of the county that is in Puget Sound that we have bare earth LiDAR for, and that'll come into play in a few minutes. So this is the whole map of all changes from 2006 to 2017. The interesting thing is if you look here, so they're color coded by change agent. Green is forestry. Purple is canopy removal. Canopy removal is a change agent because it denotes places where we don't think it's forestry. It's a small location, but we don't really know what the purpose of it is. So we don't know whether it's going to be developed or whether it's just clearing of some trees. But if you look at the pattern, it's obvious that canopy removal is associated with urban areas and urbanizing, and not with really with forestry. So again, I'll come back to the forestry thing for a minute here. As you can see, I've split out the acres of timber harvest again. And so out of a total of 367,000 acres of change through the 11 years, 70% of that, 266,000, is timber harvest, which is represented by those little green dots all over the place. So as the graphic says, the event size here has been exaggerated so that you can see them, because it's very hard to visualize 250,000 dots in a small graphic like this. I should also note that RIA 3 has been outlined in yellow there, and so if you took all of the footprints of all the changes and you squeeze them all together into one spot, it's about RIA 3 at this point. So why do we use these quantities? Why do we quantify canopy loss and impervious gain? Well, this is different from most change studies, as most change is usually done as class transitions, and so you wind up having some class goes to another class, like forested goes to urban, or shrub goes to tree, or you have different land classes and things move back and forth between them. Unfortunately, once you set up a land class system, it has to kind of emphasize either vegetation or imperviousness when you go from one class to another. And this was a real problem for us as we tried to capture the information we wanted, because we were really interested in information to monitor habitat changes. And the two things that tend to really at large scale modify watershed hydrology and habitat connectivity and all the functional processes that we're interested in are loss of canopy and increases in imperviousness. So we decided to just directly map those as opposed to trying to come up with a transition system that would capture it. Another problem with transitions is that small changes often don't lead to a class change. If you have a residential area and it's all mapped as sort of medium density urban area, and you take out a few trees and put in a house or two, that doesn't actually change the land class, and you can't capture that if you only use land class changes. In addition to these two things being quite useful and important for the type of things we want to monitor, they're also the more repeatable and easier things to observe in 1 meter imagery. And so in addition to being important, they're more accurate than other things one might measure. Yeah, and many habitat questions are affected by this. Another problem with So this is where we can have a problem with these transitions is in their definitions. So in the Anderson land cover class that is used by lots and lots of land cover mapping, forests are often defined as pixels that have greater than 25%, equal or greater than 25% canopy cover, and no impervious surface. And then the 3 impervious surface classes are defined by how much imperviousness there is. And so low intensity development is any pixel that has greater than 10% impervious surface, up until I think it's 40% becomes medium. I don't think I have that. Medium intensity and high intensity are simply higher percentages of impervious surface. So if you had 30, so these 3 rows here represent 3 30-meter pixels that might change from time period 1 to time period 2. All 3 of these represent a transition from a forested pixel to a low density development pixel. And you know, the pixel's about a 30-meter pixel is about a little less than 1/4 of an acre, which is a pretty standard housing lot in the U.S. And if you think of a lot, you think maybe 1/4 of it or 1/3 of it in a lot of places. Now with low impact development, the house will take up a much larger portion of the actual pixel. But in more traditional ones, it's closer to 1/3 or 1/4. And so in each one of these cases, we wind up with a transition that would show up in summary statistics as 100% loss in forest cover. And in fact, we have a 50% loss in the first row, 0% loss in the second row, and 100%, sorry, I knew I was doing this in a very bad way. We have 50% retention in the first row, no retention in the second row, and we retain 100% of the canopy in the third row. So we actually have a range from 0 to 100% retained canopy that all show up as the same thing in transitions. So that's why we don't use them. Another big question people have is, why don't we map habitat gains? Well, vegetation growth by design is hard to distinguish from the rest of vegetation growth. So if you go out and you plant a small plot of trees or riparian vegetation, we can't really find that as opposed to all the other background vegetation that's growing. Also, over short time periods, tree growth is not very much, so you can't really detect from observation the couple of feet that a tree might grow over those short time periods. Vegetative growth, such as annuals, crops, things like that, we don't really want to map as land cover changes, and so we can't really differentiate between bare ground in one image going to 8-foot crops in the next image versus a clear cut coming back as small trees. Those they pretty much show up as the same thing, and we don't want to. Why we would want to necessarily map the trees coming back, we don't want to map crops as land cover changes. The other type of habitat gain we might want to map are losses of impervious surface, where they're actually taken out for some reason, but that happens so rarely that you can't really effectively sample for it. But what we could do for habitat gains is if we had good maps of where restoration projects and things of that nature have been put in, we could monitor them for consistency. Okay. So data can be the change data can be gotten from our new website here at which is our new ArcGIS hub site. And if you go there, you'll see this opening page. And if you scroll down to the bottom, there is a link to download the change data from the Washington Open Data Portal. And if you go to the data tab, we'll also give you a big link that'll take you here to geo.wa.gov. And if you just go to geo.wa.gov and search for change, it'll come up. If you search for HRCD, oddly, it doesn't come up. So change is the easiest one, or just go through our website. At the website, there's a documentation tab, and at the moment, the most activity is going on at the documentation tab. Methods is honestly some reasonably old text that I wrote. And the projects tab pretty much gives at the moment a enumeration of the different projects that have gone into producing this. The FAQs actually are new, and probably I should have had a slide for that on here. So documentation, we have a couple of we have a cheat sheet and a fact sheet that both are sort of single page information to try to get you up to speed. The user guide is quite a bit longer and is more of a narrative on how to use the data, and gives some additional information about the new reporting system we have. So this is the fact sheet and the cheat sheet that you can download, put up on your wall to gaze at lovingly. Then we have a new section. We're working on standardized reports by each RIA, and I guess we're also going to do them by each county. At the moment, we have a draft of the polygon analysis for change report and a draft of the accuracy assessment report. We have those separated out because the accuracy assessment can really only be done at the RIA level, and it's going to be dull to a lot of people, but it is a good documentation of the extreme amount of work that goes into making sure these are accurate pieces. Samples of both of those can be found at the documentation page on our site, and while they are supposed to be self-explanatory, they're mostly self-explanatory, but the user guide has more information to try to explain some of the nuances of using them. We will have a tree mapping report getting added, and riparian status and change assessment report that we're also working on. These will all be available on the website. At the moment, all we have are some samples, but we'll have, and you'll notice if you look at the samples that the colors and formatting and all is sort of terrible, because most of it is designed to see that our styling templates are working as opposed to actually being final products. Okay. And yeah, you can download those on the documentation page. Okay, Move on to our second topic, which is high-resolution canopy maps. So these are new and for our 2017 data, and we've been working on trying to do land cover ever since we started in 2006. And I have another document that kind of goes over our different attempts at land cover. The first ones were completely useless, and then we had a slightly better ones with phase 2, the 2009 to 2011 one, and then DNR started producing this thing which gets called all sorts of things, but it's digital photogrammetry, which is a fancy way of getting a height layer out of the NAPE data. And using this, we get a co-registered height layer, and that has helped a lot in trying to do land cover mapping. Since the NAPE data covers all of Washington, we can get that surface height anywhere, but you have to have something to subtract off of the surface height, and that's where bare earth LiDAR comes in. This is the extent. The green is the extent of where we have bare earth LiDAR in Puget Sound, which is a pretty big area. This is what we had when we were doing the mapping for this go round. Since then, we've actually gotten LiDAR for the chunk here in the Olympics that was missing, so we'll be adding tree canopy for that. The nice thing about LiDAR is while it does not get flown all at once, the bare earth you can summarize over long time periods. So while the LiDAR that makes up this extent covers stuff from over 20 years and hundreds of different flights, it works very well together for the bare earth portion, where of course the top of the canopy portion is going to be highly different for each flight, and that's what we're trying to measure. Trying to measure those changes with our program. So using LiDAR at different time periods for different heights wouldn't help with that. So here is the canopy portion of RIAs 1, 3, and 4. I usually only do one at a time, but I decided I wanted to try to show a more regional approach. So the purple is canopy. I use that because it really it helps not doing it green because it already looks sort of green. And here you can really see where green is misleading. So if you look up in RIA 1, you can see up in the north there's lots and lots of green, and those are pretty much all, that's all agriculture. We zoom in, so I wanted to zoom in a little bit kind of in the center area to give a little more idea of nuance, but it's still really hard to see what's going on at this scale. You will notice a couple of things potentially, such as this river course in here is pretty well outlined. We've got another one here, and there's sort of a reason for that, and we'll come back to that in a second as we tie in some more of the other types of data we have. Now, just to get a little more of a nuanced view, I zoomed in randomly to this spot last night about 11 o'clock when I started doing this additional set of slides. And so here we are in 2017, and I just wanted to show the different types of data. So I picked this because we have both water and trees in it, and we can see the nuance of where those locations are. So here's the tree canopy. And if I kind of pop back and forth here a couple of times, you can see that does a pretty awesome job. You might notice in this area what you may be looking at and going, I don't know if those are trees or not. And you might also notice right here in the center, that looks like some trees in rows that maybe didn't get captured. One thing you remember when you're mapping trees is that not all trees are created equal, and there is no international defined definition that separates shrubs from trees. And so when you get to that even 8-foot mark up to around the 15-foot mark, there's a lot of fudge as to what is a tree, what isn't a tree. And so it gets really hard at these scales, especially to get stuff that's that size consistently. We have a lot of single small trees that get mapped, but that's where I'd say we miss things. And part of that has to do with definition differences. Second, our other data source that we're going to talk about here is our mapped water data. And so this is with the water, we mapped both visible surface water, and we tried to capture gravel bars at the same time, knowing that, of course, this data is captured in late summer, and so flows are relatively low. And by having the gravel bar in there, we have a better idea of what bank full or what full area might be like, so that we can look at different aspects of where the water is. Plus, a lot of these gravel bar areas for bigger streams are places that the actual water can move from year to year very easily. And we see that in our next slide. I thought, gosh, it'd be a good idea to add change to this. And at the time, I hadn't really thought about the fact that this is one of the largest riverine change areas I think we've mapped anywhere in all of Puget Sound. That did actually happen randomly. But since all of this blue is canopy change over these 11 years, I thought it'd be a good time to pop through a couple of different images. And so if we go back to 2006, we see we've got all this canopy here, and stream is where it is. And then we do our 2006 to 2009 change, and it starts moving around a little more in 2011, 2013. The other thing I want to emphasize here is between each of these time intervals, we've actually done the change analysis. And so it's a lot of data with a lot of attributes. 2015, 2017, and then if we just look at all the change locations, and originally I had them color coded by the change agent, which is why all of the riverine changes showed up as blue, but here we have them color coded by the change interval. And so you can see 2006, 2009 to 2011, 2013, 15, 17, as that river edge slowly moves across the landscape over those time periods. Okay, so, and here we are back with all of the actual data and the changes on. Okay. I want to move to the final type of data that we have, and that's our mapped surface water, which I'm not going to talk about a lot, but I'm going to kind of help bring into context once you put all this data together, the sorts of things that you can do with it. So as part of 2017, we mapped the visible surface water in the 2017 NAPE imagery for all of Puget Sound. This turned out to be a much larger task than I naively thought it was going to be when I started. And part of that is because we had a bit of scope creep as to what we actually wanted to map once we got started. We realized if we were going to do this all at once, it would be good to try to get everything that was visible and not just the river courses. And so there it is. Now it's done after about 1.5 years of miscellaneous working on it. If we go back to this mid-region slide from previous, and now in addition to the trees, I've added in the surface water. This is effectively what our land cover data is at this point. It's these two quantities. We have tree cover mapped and we have surface water mapped. And actually the reason we started mapping the surface water was to do a better job with the tree canopy, because the height data we get from DNR, since it's based on multi-image processing, it's sort of I won't say it's an AI type thing, but it's gathered from looking at different angles of photos. It has a terrible time with homogeneous surfaces because it can't figure out what's different in the two images. And so in order to fix the homogeneous surface problem, which most frequently happens over water, we started mapping water so that we could fix the canopy. Anyway, almost 2 years later, it's done. And so that is what our land cover is primarily. I thought I'd throw the imagery up so you can kind of see where the trees are in the water. And then we can see change as well. So these are all the change locations. Green is forestry change. Purple is tree removal, and orange is development. Development is generally any kind of small change that, or any kind of any size change that has new impervious surfaces associated with it. And a tiny bit of blue, you can see where those stream changes are. And if you throw this all together, you almost make your computer die, as it almost died trying to make this slide. So now we have millions and millions of individual polygons on the screen here. And that brings us to a little bit to the nuances of the types of analyses you can do with this data, because at each location you've got 4 different change quantities you can be interested in. There are 8 different change agents that you can cross these different quantities with. There's initial land cover, and there are 5 time periods. And then you can relatively easily look at, and then we also have, the area of the polygon and what raya it's in, and we're going to add what county it's in as well. But you can ask really nuanced questions, such as, where are the 10 largest locations of canopy removal after 2013 in Raya 6 not associated with forestry? There are just many different dimensions. And there's a lot of nuance in asking some of the questions. So the way you might go about and then beyond that, you get into the really interesting stuff, which is where you interact with other data. And so if we take our change data, and yes, I realize in this particular case, it's all our data, but there are lots of other data sources, which I'll touch on here in a second. But so here we take a notion of critical areas, which is going to be just a really simple 100-foot buffer on all of the SWFTI data, which is the statewide integrated fish data set, and our surface water data. If we put a 100-foot buffer on those and then intersect that with the canopy, and then intersect that with the change data, we can start to get an idea of change within riparian areas to canopy. And you could do that same type of thing with lots of different ancillary data sets, and each one of these will have its own nuances of things one could ask, and there are a lot of them out there. We're going to have a quick example looking at hydrology data here, and that'll wrap us up pretty well. So these are the poorly realized riparian areas that I did for this quick and dirty analysis. A couple of things that I realized when I looked region-wide is that I used all of our surface water data, and about halfway through the surface water mapping, we started mapping near shore to try to get away from the trying to pick what to do when you get near to the mouths of rivers. And so some of the rayas have near shore and some of them don't. And so in the summary statistics, that shows up in the area we mapped as riparian. There are also other types of surface water in here that we probably don't want to map as riparian to do a really good analysis. So as I say, this first one is a quick and dirty idea that gives you sort of a notion of what rates and things are. So we have riparian change here by raya for all of Puget Sound, except for at the time I did this original table, we hadn't gotten the Upper Skagit or Island County done. They are actually done now, but I didn't have time to add them under the table. So here we have by watershed or raya, the number of locations of change that occurred within the riparian zone over the 11 years. Actually, I take that back. This is over the 2 years. Yes, this is the 2-year data. The change in acres in the riparian zone in each one of these rayas, the total area of riparian habitat, an annual change percentage, and here we see they range from 0.11, I think is that is 0.11% per year. So yes, that would be 10 years to roughly 10 years to modify 1%. Up to a max of 0.56 in Puyallup. I bet you there was now one thing. So here's one of the nuances. this includes natural changes as well as anthropogenic changes. So one of the things you could start breaking out is natural versus anthropogenic, and that will give you a different change rate. And then the final piece I have here is canopy percent. So based on the way I map riparian for this analysis and the way we map trees, we can see that our range of canopy percentages for our riparian areas goes from about 46% up to 91%. And again, some of those, this is by Ryan, not by county. Okay, I did this by county in a different place, and of course you have to remember that not whole counties are in Puget Sound, and lots of different sub pieces that go into doing a great job with this type of analysis. And there are lots of comparisons one could make. This is just a few I came up with quickly. You can look at change inside versus outside incorporated areas, or you can look at change in the riparian zones using any of these additional anthropogenic or any of these additional ancillary bits of information. You can look at natural versus anthropogenic. I guess I see where I got some of the ideas for the last example from. You look at how many natural stream changes result in new riparian forest. So this was interesting. By using the change data, you could buffer the change data to find out where the changes in riparian habitat result in new locations that still have trees around them. So that might be an interesting way to go after that. Lots of different ways to spin these different data sets. This reminds me of one thing you can do is, since we have the 2017 tree map, you can use the amount of change that occurred prior to 2017 to back calculate how much riparian area there was previously, which is the second part of this this idea. And the first idea was an anecdote I got from Robin Hale, one of our other LSA employees, who is doing a lot of this work and helping us out. And she noted in Lewis County's analysis, they used the largest impervious change locations to look for what the context might have been, and they found that there were some locations where large new impervious were actually warehouses where they were putting, I think they were manure warehouses, and so the actual new impervious was a farming practice that was getting erosional farming waste out from under natural areas, so that it was actually the impervious surface was actually improving the local area by reducing runoff. That was quite a tangent that I probably should have practiced better. Lots more analysis being done. We have there's another NTA that's being done by WFW to look into stakeholder discussions on how best to deal with some of this nuance and automate more of the reporting so that people get what the data that would be most useful to them to try to handle that. We have a grant for the science panel to do a hydrology and riparian status and error analysis, and there'll be a lot more on that coming up. And finally, we have another NTA trying to develop a framework for assessing ecologically important lands. And so those are all new things that will be coming. And that is it for my yapping. Thanks.
Thank you, Ken. We have lots of questions, so we will I will try and go through them and send them to Ken to get through as many as possible. And those of them we don't get through, we'll make sure to share with Ken, and if he's able to point us to how to answer them best, or to make minor additions to the slides that we share after this presentation to address your questions, we'll do that. So. And there's a mix of highly technical questions and bigger picture policy or and management questions. So I'll try and scatter in a mix of both of those. All right. Let me get to where. So I think maybe just a few basic technical questions folks had. Just to clarify for folks, we got one question: is the river moving going to show up as loss of forest cover? or when you were giving your river example. You are muted.
There we go. Yeah. So the river. So what we mapped, and this is a good thing to talk about. What we mapped was really the tree river interface, and so what we're mapping is what we actually see on the imagery, and so we can't. So we aren't mapping the actual bank, because the actual bank is really frequently. Oh, we are sometimes, but is really frequently underneath canopy. So that is the issue there. So good clarification. The map of surface water you see is really the reason we call it, and we actually call the data set the visible surface water, is it's what we're seeing visibly in the imagery. So yeah, we are not getting the overhang very well, but we think we generally have a better note of where the edge of the bank we have a better map of the tree forest interface than we get from previously older like NHD stream banks.
Thanks, Ken. All right. Bigger picture question. After spending the time you have getting familiar with these data, what are the most profound or surprising insights you have gained about change in urban areas, particularly as it relates to tree canopy cover?
Well, I'm gonna answer that in two ways. One is I really don't get that much time to analyze the data. It's pretty much a constant rush to keep it getting pushed out. So I haven't got a lot of great nuanced analyses, which is why I listed them as opposed to showing all of them. But the thing that does consistently show up and has been consistent through all the whole time period is that change rates are actually pretty low. They're not terribly high. They are on the order of magnitude of less than 1% per year, and they tend to be in the times where we've done comparisons of riparian change to outside of riparian area changes. The riparian areas tend to always have lower change rates than what's outside of them. We've done a shoreline analysis using the 200-foot border for the whole Puget Sound shore, and the change rate in that 200-foot border, which is covered by the Shore Management Act, is lower than it is outside of it. And so I guess the most profound thing I think we see is that we think a lot of our rules and regulations and critical area ordinances are doing a pretty good job overall at maintaining those areas that they're trying to maintain. But there's lots and lots of stuff to be asked and figured out that hasn't been done yet.
Thanks, Ken. Are you able to talk a little bit about, so we had a question that says the data seems backward looking, as in what's already happened. Is there a way to use the data for forward looking analyses?
Oh, well, I guess the most useful, you do two things. One is considering how consistent the change rates tend to be, you could extrapolate them out into the future, and that's probably a pretty safe bet because there hasn't been a lot of variation, at least at large scales. The other thing one could do, given some kind of a driver, you could go back and say, because you've got the 5 different time periods and you've got change in a lot of locations, if you had some kind of driver through time that you wanted to try to relate change to, you have the information you need to try to do it. So if you wanted to say, you put a new road in and you want to see how quickly houses pop up after the new road goes in, with only 11-year time period, you're not going to find a lot of locations of that. But hopefully, if this data continues, those types of analyses will be facilitated with longer term data. You could certainly do it now. So yeah, that's my answer to that for the moment.
Thanks, Ken. have a question asking, is the program sustainably funded by the state so it continues to incorporate future years of data, or does it need EPA funds? And there's a comment saying the state should fund it.
Yeah, no. I'm just going to go with no. It's each one has been an individual scramble for soft fund money, which has mostly come through the LIOs, and they've been a steady supporter of this work all along. But we don't. There is now 2019 data, and we have zero funding for Puget Sound to work on it. That may be partially because I didn't put an NTA in. Because the last NTA go-rounds were prior to that data coming out, and that's a nuanced question, and I'll just leave it at that.
Thanks, Ken. I've got a long question from Will Hall here, so I'll try and read it, and I'll also publish it so you need to refresh your memory. So Snohomish County is asking the Puget Sound Regional Council to amend the regional growth strategy to plan for an additional 12,000 people living in the rural area. This would require 4,600 lots outside the urban growth area. And so on average, each new rural lot developed in Snohomish County clears 1.5 acres of forests and adds 0.4 acres of impervious area. So he's done some math. So that's about additional 800 acres to be cleared, of which about 4 million trees. And it would pave, according to Will's rough math, about 1,800 acres in the rural area. So the Puget Sound Regional Council will be making a decision in the coming months on whether to approve this. And he's asking, is there a way your work could inform policy decisions like this?
Well, that's the design of our work, is to inform policy decisions such as that. I will be honest, I didn't catch the whole question because my hearing's not that great. And if I could read it at the same time, that would be a little easier. But in order to inform a question like that, you really have to look at what are the policy drivers that you're trying to ask the question about, and then formulate the analyses that support that. And I'd be happy to talk with anyone trying to come up with that analysis to think about the data in ways that would inform that policy decision. That is sort of the next real place where a lot of this data has to go, is that it's a really new and completely different data set, and I don't think anybody has a data set like it anywhere else to have ever done any work with to try to answer any questions like this. The intent when we designed it was exactly to do that sort of thing, but it's very tough to get the whole science policy interaction to get from creating the data through to how that data informs policy to actually having policy informed by it, getting all those people together. And that is why we have webinars like this, to try to help bring the folks together that it would take to insert data into the policy process.
Thank you, Ken. Switching a little bit back to a slightly more technical question, but one that has relevance, I think, to the policy lens, which is there an easy way to show man-made cause changes compared to natural causes?
Yeah, it's in the data set. There's that was one of the reasons we do the change agent, is so that you can separate out. There are two natural causes, and they are streams, because streams are the most common one, and other natural. And other natural tends to be mostly fire and landslides. There are some others. There's some tree kill and things of that nature. But yes, that is in the data set, so you can separate out those things.
Thanks, Ken. There's a question asking, are there plans to go back even further, say back to 2000 or even earlier? Is that possible with the data that are available?
Yeah, it's not really possible with the data available. We could to some extent do it if we found, let's put it this way, we could probably find aerial imagery for most of Puget Sound from earlier. We wouldn't have it all in the same year, so to speak. So you could piecemeal it back further, but it would be a lot harder and probably a lot more expensive. And my sense of things is really that the historical data is super cool and it's fun to look at. And if you want to go back to an older policy change and make a case that policy change had a strong effect, yeah, I understand those desires, but it seems to me that what we're really worried about is what's happening, what the dynamics are happening today, what going forward is like. So we want to be able to change policies as they are relevant to current conditions and current dynamics. And so we value, as a program, we value current high resolution, high temporal resolution data over longer term historical data.
Thank you, Ken. All right, we are at 11 o'clock. We've got lots of questions that I know we did not answer. So I do recognize that. Thank you all for so many really great and detailed questions. And we have a log of all these questions, and we'll see what we can do to pull together when we release this recording of the webinar and the slides on our website, which you can see there. There's the Habitat SI grant program, and the second link is for our strategic initiative website, which we'll also publish for you in the comments. We will see about finding if we can also share some answers to some of those other questions, or a summary set of answers that are kind of synthesis of the common questions we got from you all. So with that, you can see Ken's contact information, as well as our team's lead on this topic, Libby Geyer, on the screen as well. And we're so excited to have you here today. And thank you so much, Ken, for sharing all of your work with us.
Thank you.
All right. See you all later.